Hi, welcome to the next section of this course, Visitor, State, Mediator, and Observer Design Patterns. In this section, we're going to look at 4 more design patterns. We'll start with the visitor pattern, which is very useful when you want to abstract away some functionality from a set of objects. Then we'll move on to the state design pattern, used commonly to build finite state machines, that is FSM, and also we will learn about the mediator design pattern. Finally, we will look into the observer pattern, which is commonly used in event-driven architectures and is gaining a lot of traction again, especially in the microservices world. Now we move on to the first video of this section that deals with visitor design patterns. In this video, we are going to delegate some logic of an object's type to an external type called the visitor that will visit our object to perform operations on it. Then we will emulate an online shop with a few products. In the visitor design pattern, we are trying to separate the logic needed to work with a specific object outside of the object itself. So we could have many different visitors to do some things to specific types. For example, imagine that we have a log writer that writes to console. We could make the logger visitable so that you can prepend any text to each log. We could write a visitor pattern that prepends the date, the time, and the host name to a field stored in the object. With behavioral design patterns, we are mainly dealing with algorithms. Visitor patterns are not an exception. The objectives that we are trying to achieve are listed here. The first and foremost is to separate the algorithm of some type from its implementation within some other type. Secondly, to improve the flexibility of some types by using them with little or no logic at all, so all new functionality can be added without altering the object structure. And lastly, to fix a structure or behavior that would break the open or closed principle in a type. You might be thinking what the open or closed principle is. In computer science, the open or closed principle states that entities should be open for extension but closed for modification. This simple statement has lots of implications that allows building more maintainable software and less prone to errors. And the visitor pattern helps us to delegate some commonly changing algorithm from a type that we need to be stable to an external type that can change often without affecting our original one. We are going to develop a simple log appender as an example of the visitor pattern. Following the approach we have had in previous sections, we will start with an extremely simple example to clearly understand how the visitor design pattern works before jumping to a more complex one. We have already developed similar examples modifying texts too, but in slightly different ways. For this particular example, we will create a visitor that appends different information to the types it visits. To effectively use the visitor design pattern, we must have 2 roles, a visitor and a visitable. The visitor is the type that will act within a visitable type, so a visitable interface implementation has an algorithm detached to the visitor type. So we need 2 message loggers, message A and message B, that will print a message with an A or B respectively before the message. Also, we need a visitor to be able to modify the message to be printed. It will append the text visited A or visited B to them respectively. Now that you are well aware of what we want to do in this video, let's start with the unit tests. As we mentioned before, we will need a role for the visitor and the visitable interfaces. They will be interfaces. We also need the message A and message B structs. I have created 2 files, visitor.go and visitor_test.go, within the folder named visitor. Open the file, visitor.go. Let's start adding the code. First, we add the package name, import statement, structs, and interfaces. The types, message A and message B structs, both have a message field to store the text that they will print. The output io.writer will implement the os.stdout interface by default, or a new io.writer interface, like the one we will use to check the contents are correct. The visitor interface has a visit method, one for each of visitable interfaces message A and message B type. The visitable interface has a method called acceptVisitor that will execute the decoupled algorithm. Like in previous examples, we will create a type that implements the io.writer package so that we can use it in tests. Close this file and move to the visitor-test.go file. Here we first add the package name, testing helper struct, and a function, test helper. The test helper struct implements the io.writer interface. Its functionality is quite simple. It stores the written bytes on the received field. Later, we can check the contents of received to test against our expected value. We will write just one test that will check the overall correctness of the code. Within this test, we will write two subtests, one for message A and one for message B types. Let's do this. OK. We will use a test helper struct and a message visitor struct on each test for each message type. Now let's first add the code to test the message A type. Done. This is the full first test. We created message A struct, giving it a value, hello world, for the message field, and the pointer to test helper, which we created at the beginning of the test. Then we execute its accept method. Inside the accept visitor method on the message A struct, the visit A message, A method, is executed to alter the contents of the message field. That's why we passed the pointer to visit A method. Without a pointer, the contents won't be persisted. To test if the visitor type has done its job within the accept method, we must call the print method on the message A type later. This way, the message A struct must write the contents of MSG to the provided io.writer interface, that is, our test helper. The last part of the test is the check. According to the description of the acceptance criteria 2, the output text of message A type must be prefixed with the text A, the stored message and the text visited just at the end. So for the message A type, the expected text must be, in double quotes, A: hello world, and in parenthesis, visited. This is the check that we did in the if section. The message B type has a very similar implementation. Let's write the code for message B type. In fact, we have just changed the type from message A to message B, and the expected text now is B: hello world, in parenthesis, visited B. The message field is also hello world, and we also used the test helper type. We still lack the correct implementations of the interfaces to compile the code and run the tests. The message A and message B structs have to implement the accept visitor method. Let's save this file and go back to our visitor.go file. So here, let's add the code to implement the accept visitor method for message A and message B. Perfect. Next, we add the code for the implementations of the visit A method for message A and message B that are declared on the visitor interface. The message visitor interface is the type that must implement them. Finally, we will create a print method for each message type. This is the method that we will use to test the contents of the message field on each type. Let's do it. Now we can run the tests to really check if they are failing yet. So, let's save the file. Open the terminal. Run the command gotest-v. The outputs of the tests are clear. The expected messages were incorrect because the contents were empty. It's time to create the implementations. We will start completing the implementation of the visit A message A and visit B message B methods. Open the visitor.go file. In the type message visitor struct, add this line. Similarly, we do this for message B. Cool. Its functionality is quite straightforward. The fmt.sprintf method returns a formatted string with the actual contents of m.message, a white space, and the message, visited. This string will be stored on the message field, overriding the previous contents. Now, let's develop the accept method for each message type that must execute the corresponding visitor. This small code has some implications on it. In both cases, we are using a visitor, which in our example is exactly the same as the message visitor interface, but they could be completely different. The key is to understand that the visitor pattern executes an algorithm in its visit method that deals with the visitable object. What could the visitor be doing? In this example, it alters the visitable object, but it could be simply fetching information from it. For example, we could have a person type with lots of fields, name, surname, age, address, city, postal code, and so on. We could write a visitor to fetch the name and the surname from a person as a unique string, a visitor to fetch the address info for different sections of an app, and so on. Finally, there is the print method, which will help us to test the types. We mentioned before that it must print to the stdout call by default. Let's add the print method next. It first checks the contents of the output field to assign the output of the os.stdout call, in case it is null. In our tests, we are storing a pointer there to our test helper type, so this line is never executed in our test. Finally, each message type prints to the output field, the full message stored in the message field. This is done by using the fprintf method, which takes an io.writer package as the first argument and the text to format as the next argument. Before you save the file, remember to include fmt and os in the import statement. Our implementation is now complete, and we can run the tests again to see if they all pass. Now, save the file. Move to the terminal and run the command gotest-v. Everything is okay. The visitor pattern has done its job flawlessly, and the message contents were altered after calling their visit methods. The very important thing here is that we can add more functionality to both the structs, message A and message B, without altering their types. We can just create a new visitor type that does everything on the visitable. For example, we can create a visitor to add a method that prints the contents of the message field. Let's go back to visitor.go. At the end of the code, add the message field visitor printer struct. So, we have just added some functionality to both types without altering their contents. That's the power of the visitor design pattern. Now we will develop a second example, this one a bit more complex. In this case, we will emulate an online shop with a few products. The products will have plain types, with just fields, and we will make a couple of visitors to deal with them in the group. First of all, we will develop the interfaces. Open visitor.go and the interfaces. The product info retriever type has a method to get the price and the name of the product. The visitor interface, like before, has a visit method that accepts the product info retriever type. Finally, visitable interface is exactly the same. It has an accept method that takes a visitor type as an argument. All the products in the online shop must implement the product info retriever type. Also, most products will have some common fields, such as name or price. Now we'll create the product type, implement the product info receiver and visitable interfaces, and embed it on each product. Let's do it. Now we have a very generic product type that can store the information about almost any product of the shop. For example, we could have a rice and pasta product. So next we add the rice and pasta struct. Each has the product type embedded. Now we need to create a couple of visitors interfaces, one that sums the price of all products and one that prints the name of each product. Here we add the code for it. The price visitor struct takes the value of the price variable of the product info retriever type, passed as an argument, and it adds it to the sum field. The name printer struct stores the name of the product info retriever type, passed as an argument, and appends it to a new line on the product list field. Time for the main function. Let's add the main function. We create a slice of two visitable objects, a rice and pasta type, with some arbitrary names. Then we iterate for each of them using a price visitor instance as an argument. We print the total price after the range 4. Finally, we repeat this operation with the name printer and print the resulting product list. Let's go ahead and check the output of this main function. Save the file and move to the terminal. Type the command go run visitor.go. Okay, this is a nice example of the visitor pattern, but what if there are special considerations about a product? For example, what if we need to sum 20 to the total price of a fridge type? Okay, let's write the fridge structure. Let's go back to visitor.go and write the fridge structure. Over here. The idea here is just to override the getPrice method to return the product's price plus 20. For this, we add the next lines of code. Unfortunately, this isn't enough for our example. The fridge structure is not of a visitable type. The product struct is of a visitable type, and the fridge struct has a product struct embedded, but as we mentioned in earlier sections, a type that embeds a second type cannot be considered of that latter type, even when it has all its fields and methods. The solution is to implement the acceptVisitor method so that it can be considered as a visitable. Let's rewrite the main function to add this new fridge product to the slice. Since we added a third product, let's change this value to 3. Everything else continues the same. Running this new main function produces a different output. Let's run the test and check it. First, save the file and move to the terminal. Run the command go run visitor.go. As expected, the total price is higher now, outputting the sum of the rice, the pasta, and the fridge. We could be adding visitors forever to these products, but the idea is clear. We decoupled some algorithms outside of the types to the visitors. Superb! In this video, we have seen a powerful abstraction to add new algorithms to some types using the visitor design patterns.